The purpose of this webinar is to discuss best practices for MBR screening. My name is Tim Mathias, and I'm a business developer for Hydro-Dyne. And an outline of what we're going to discuss in this webinar includes a background for MBR screening, some design requirements, followed by design strategies. Then that leads to best practices with screening design for membrane bioreactors, and then followed by a case history. Then we'll wrap it all up. And you're looking at two pictures here, the top picture being vertical screens in front of an MBR process. And the second picture on the bottom is a immersed hollow fiber membrane as it's been pulled out of the treatment process. So without further ado, we talk about what is a membrane biological reactor. Here's a common configuration. We have two tanks. So flow comes into an anoxic and aerobic zone, followed by an immersed hollow fiber membrane cartridge, which sits in its own tank. Air is added to both tanks. And the drivers for this process include better effluent quality, a smaller footprint, and water scarcity. So as we make better water, that drives, if we have water scarcity, that can drive more water recycling. And the trends worldwide are that this process is growing. We have larger sizes of plants with MBR up to 100 MGD. It's a more accepted technology as we move forward. So there are more sites, more companies, more applications, and more products. So we have increasing public acceptance of reuse, and that's also driving better water quality and better wastewater treatment with this process. A little bit more background and some quick facts. Most prevalent technology currently is the immersed hollow fiber membrane. There's a picture of a cartridge to the right. And what we have here are fine pore sizes. And the pores function as a barrier for water solid separation. The pore size, if we look at a picture here under an electron microscope, is zero point 0.2 to zero point 0.4 micrometers. That's a thousandth of a millimeter. So very, very small pore sizes. The material that the membranes are made out of is polyvinylidene fluoride, so it's a highly non-reactive material that can be chemically and physically cleaned. The membrane rejects small solids, and air is used to scrub the membrane surface. And in some designs, there's a flow back pulse that's used. So pores can become clogged and fouled, and fibers can get caught in that very small matrix. Talk about that for a minute. Fouling is the coating of the membrane surface with colloids or fine solids. Clogging includes solids that enter the pore matrix and block off flow. Braiding includes textile fibers that become entangled in the pores, and that can block flow. So looking at loss of flow, we can have a fouled system or a clogged system. Fouling is somewhat reversible. So chemical cleaning can be used for that. And if fouling is irreversible, then the membrane cartridge has to be pulled and physically cleaned. And clogging and braiding also have to be physically cleaned. So there are three methods for limiting fouling, the first two of which are operational to the wastewater treatment. And the third, of which we're going to discuss today, is screening. And you're looking at a fouled cartridge with this picture. This shows a combination of fouling, clogging, and braiding as that has occurred on the membrane surface and has to be physically removed. Looking at the process again, we have screening in front of the wastewater treatment process. And in this case, the immersed hollow fiber membrane cartridge sits in its own tank. So if we have good screening, the benefits are less membrane cleaning, and that means chemical and physical labor required, or chemical cleaning and physical labor required to clean the membrane surface. And then ultimately better pump operation downstream. There is less textile fibers that can get caught and bound up in a rotating pump impeller, and therefore less maintenance required over time. So good screening is important. Let's look at an actual view of a pretty large plant. And we can see on the left the screening facilities, and on the right, the wastewater treatment facilities. And focusing on the blue square, we have screening, sluicing, compaction, and grit removal all in that facility. And to the right, we have the base wastewater treatment, which includes anoxic and aeration basins, followed by a membrane basin. We're going to focus on the screening. And looking at design requirements required to protect a membrane biological reactor, the screening is set up to manufacturer spec. So it's generally very small spacing required, and this is for most immersed hollow fiber and flat sheet ceramic membrane systems. Also, capture counts. So the idea is to remove as much total suspended solids as practical coming into the wastewater treatment process. We also never want to bypass the screening system to protect the membranes. We want to maintain low grid velocities and have the best offload so that we can clear the screen as it picks up and captures material. Ideally, we can maintain low head loss at peak and average flows. Footprint is important. We want a facility with low footprint if possible. We want to utilize best screening offload methods, and we want corrosion resistant materials. We want to optimize dewatering equipment, and then any controls that are special have to be accommodated. So that can be grouped into design strategies. And design strategies include maximizing capture. That means removing the most material, and that's unwanted inorganic material that we can from the treatment process, and some other key factors, including footprint, grit removal, and offload. So we're going to move into best practices, and the best practices are grouped sort of toward design strategies. Looking at the first best practice, if we have solids capture, we want dual stage solids removal. And that's in cases where there is no primary clarifier and we have larger plants greater than 1 mgd. Small plant can handle a single stage in screening, but larger plants require 2 stages, generally as practice. So why is that? Fine screens can be overwhelmed by peak flows. Also, coarse screen reduces the load on the fine screen, as you can see squared here as the second stage. And then if we design the system correctly, the solids removed by the coarse screen stage are equal to the solids removed by the fine screen stage. So we equalize the loading between the two stages and use the coarse screen as a working screen to pull off some of the solids. We also never want to bypass the design, the screening system. So that means redundancy is required generally. And typically redundancy is in an N+1 configuration. So if it takes a single screen to process, say 10 MGD, then we would do N+1 or 2 screens to protect our MBR process. So I want to talk about the fine screen grid first in the two-stage system. The fine screen grid is determined by membrane type. So in this case, most hollow fiber membrane types require 2 millimeter spacing in the grid, and that's to remove fine material before it hits the wastewater treatment and the membrane surface. Some hollow fiber membranes need to be screened at less than 2 millimeters, 1 millimeter or less in spacing. Mesh panels are required for that. We'll talk about that in a minute. And then some flat sheet membranes are a little more forgiving and they require 2 millimeter spacing as well. Looking at the grid needed to achieve the proper screening, we look at a perforated grid on the left, and this is done in ultra high molecular weight polyethylene, so it's a non-ferrous material. Then in the center, we see a perforated grid to 2 millimeters. That's a very common grid for membrane processes. And this material is in stainless steel with holes that are machined into the stainless steel. And then we have a woven wire stainless steel mesh, and that's for very small grids needed in some applications. And moving on to best practices with respect to capture. And in this case, looking again at the fine screening stage, looking at equipment types. So the equipment required here has to have the highest capture available, and that's generally required by the membrane manufacturers. And if we define capture, that's the amount of material that the screen removes in total from the wastewater treatment process. And that means suspended material that's organic and inorganic that's taking out of the front end of the process. And with fine screens, equipment has been tested by the UKWER. This is the United Kingdom Water Industry Research Organization. And I won't go into the details on the testing, but they've determined the highest capture screens are drum screens and a center flow band screen. So these are generally used to protect MBR processes. So let's focus on those types of screens. And we're talking about the second stage first here in the fine screen before we talk about the coarse screening stage. So as we said, fine screening requires high capture equipment. And looking at the ratings for drum screens and center flow band screens, they've been rated as high as 93% at 2 millimeter spacing. So they can take out most of the debris that is in the system before the membrane tanks. And it goes higher actually with smaller mesh ratings. So in considering the drum screen first, the drum screens are called generally horizontal options. So we have a seal at the inlet and the outlet. There's no intermediate seals with the drum screens. Drum screens have been used for a period of years, and there are many applications with respect to MBR screening. Generally, drum screens are inclined and they can rise to 10 feet, 3 meters in diameter. Drum screens can be rated at give or take 10 MGD each, but that's about tops for each unit. And a large footprint generally is required as the drum requires large and wide channels. Some drum screens are marketed specifically to MBR, so they're designed specifically for membrane processes and have the spacing needed to accommodate that. Moving on to the next screening design that is approved for membrane treatment. There's another example of a drum screen setup. We have a center flow band screen. This is another high capture design. In this design, the screen needs to be designed at a high precision, and that means that if there are any intermediate seals, they have to be designed to hold a 0.5 millimeter tolerance. Center flow band screens can be rated very high to 100 MGD. Generally, all maintenance is above the channel, and you can see the animation here. We can see material as it comes into the barrel of the screen and is picked up by the grid. It's a vertical design, so generally these designs have very small footprints and can be accommodated in narrow channels. So we should look at some examples of both screen designs. So moving forward to a drum screen design, we see an overhead view. This is the same plant. I've used North Las Vegas here. It's rated to about 25 MGD. We can see stage 2 with fine screens. These are inclined drum designs. We can see the 4 drum designs. They're quite large, needed to accommodate the flow. Wide shallow channels are noted here with an elevated building. And if we look at stage 1 to the right, we can see that the vertical design in this case allows for higher flows and generally a smaller footprint, and the building in the center is for solids removal. Moving on to another example, this is a plant in Pennsylvania that upgraded its system to an MBR process. So therein they needed to upgrade screening, and in this case, you're looking at the circle, and that's the fine screening building required. And looking at a picture of this, we can see what that building looked like when it was done. And then moving on to the internals of the building, we see in this case, center flow band screens were used. About the same flow rate in this case. I think we went to 30 MGD. And here's a picture of the actual screens. This is the top end of the vertical band screens. And this was post primary clarifier. So in this case, in this process, only one screening stage was used with redundancy in 2 screen equipment pieces. And the grid here was used as 1 millimeter mesh. So in this design, there were narrow channels, and that provides better turndown. And what that means is the velocity profile for the screen is better at higher and lower flow rates. So there's a wider spread in flow that can be accommodated. And it's probably noteworthy to look at a footprint comparison between the 2 screen types. As we get to these larger flows, the vertical designs tend to provide advantages. So in this case, you're looking at the vertical design in the red circle, followed by blue circle here with the um, drum or horizontal design, and it's about double the space. And this doesn't consider the solids handling equipment that would also be added onto this design. So it just gives a sense for the size and scope needed for the different screen equipment types here. Moving on to the course screen, there are many equipment types that are available for course screens, so lots of choices here. And we have a best practice, and that would be to optimize the grid of the course screening system first. So to do that, let's look at the wastewater and what can be variable. So for course screening, what this screening stage can pick up really depends on the collection system. And collection systems are very different from place to place. They can have many pump stations, many pump types. They can include grinders to grind up the flow into small pieces. We can have industrial flows. We can have seasonality with high flows in the summer or winter and low in the summer, low in the opposite season. In some places, water and weather matters, so we can have rain or lack of rain, which concentrates the system. And in some systems, we pick up a higher concentration of fats, oils, and greases, and wipes and rags. So all that can greatly vary from place to place. So rather than just picking a spacing for our course screen, we would advocate to use site testing here. So we found that a decrease in grid spacing by a little as 2 millimeters can make a big dent or a big increase and change in the amount of solids captured by a system. So with site testing, what can be done is we can test many different combinations and determine and optimize the best combination in spacing and grid type to optimize capture between one or two stages. So to the right here, we see a side stream sieve test arrangement. And this is where flow is taken out of a wastewater treatment process. It's processed through screening stages and then back into the flow. And you see the table here with 50 some odd tests of various screening grid combinations. So we can characterize and quantify the screenings loading of each combination. We can look and find the best dual stage setup or single stage setup, should that be the case. So we can optimize for capture here. And then this also helps us with equipment sizing, because once we pick the grid, then we can understand how that grid needs to be deployed for best capture design. The stream test, it also should be noted, can be used to measure screen performance after startup. So the best combination here represents low differential pressure with high capture. And just looking at the results, if you look at the bottom picture, you can see these are visuals of the amount of material captured in the sieve stages for side stream testing. And that material is then weighed to determine what combination picks up the most material at the lowest pressure drop. And we have pressure curves that are generated over each one of the stages so that we can optimize drop in pressure and head loss versus the amount of material picked up. Looking at an on-site screening apparatus, we can see piping to the left that is used to pull material out of a wastewater treatment channel as it comes into a plant through a sieve arrangement. And then pressure and flow data is taken before that wastewater is put back into the plant. And looking at the course screening stage, which is the first stage of our two-stage generally screening arrangement for MBR processes, there's a wider selection of grid types and sizes here. So slotted bar can be used and perforated plate. We generally would not use wire mesh screens in the course screening stage. So the idea here is to fit the equipment to the best grid selection. So once we've done our testing to determine what that grid looks like, then we can pick the best equipment, which gives us things like best capture, best head loss, lowest head loss, low footprint. We want to consider the solids handling material as we pull screenings off, and that generally it would be nice to have a low footprint for that. We want to use the best offload methods. Obviously, capital cost is a consideration. O&M requirements are a consideration. And looking at all of these factors, a life cycle cost evaluation is advocated as a best practice. So moving forward, looking at grit removal. So grit removal is typically placed after the coarse screening stage and before the fine screening stage. This flow diagram does show redundancy in this. So we see two trains here. In this case, or in many cases, vortex grit removal is common for MBR protection. See our bubbles. Let's look at that in practice. So in this case, we have a design that's rated for 17 MGD peak. And we have determined that a 6 mm grid here followed by 2 mm is a good design. And we can see narrow channels for the coarse screen, which is stage 1 on the interior, going to the round vortex basins and then followed by fine screens. And it's of importance to note that the footprint in this case is extremely small. So for a pretty large plant. And it might be worthwhile looking at the footprint differences in a little bit more detail. Here we see the horizontal drum screen alignment, and we can see about 23,000 square foot needed to accommodate screens, coarse screens, and solids removal. If we compare that to a vertical arrangement with a larger plant, you can see a much smaller footprint is needed, up to 5 times less. That's a good comparison for a large plant. So it's also important, once we've picked our screening equipment and grids, that we have conservative hydraulic design. And this means that our flows, when we design the screens, would be used as peak flows. And also our downstream water depth sets the screen area. So it's important to have a good understanding of what that water depth would be limited to. And then we design for a conservative obstruction. So it's important that we develop screening calculations or calculations for screening and head loss, so that here in this case, if we look at variable screening blockage, we can understand the head loss as the screen gets bound. And it's important to note the green line is the channel velocity. That's greater than 1 foot per second, and that's used such that grit does not accumulate in front of our screen. Same thing with the outlet velocity. Accumulation in grit can wear out the screen, so it's important that we carry the grit to the grit tank. And the grit velocity here, as shown in gold, is generally less than 4 foot per second. And that's important because we want to be able to offload the screen and we don't want to carry too much material to get bound into the screen. In this case, screening design, one needs to pick a screen obstruction point so that we have a conservative head loss at a point when the screen is blinded, and we would generally advocate for 65% at a minimum. And here we had 16 inches of head loss as an example. Moving on to screening offloading. Offloading is the key to a good operation. These are more advanced designs, so we're not talking about having rakes that would go over the screening grid. In this case, high pressure water is used to remove and clear the screen grid so that it can be used to pick up debris again. High pressure water in some designs can go, if we look at the mesh grids, can go as high as 1,000 PSI intermittent washes. So there are some designs that do incorporate that high pressure wash into the equipment. The offloading nozzles and spray apparatus needs to be easily serviceable. It needs to be easily inspected such that in a short amount of time, one can determine if nozzles are all working correctly. So the solids backwash into a hopper, then the wash water continually flushes screenings to an extended sluice or directly into a washing compactor. This gives an example to the right of how the sprays would be used to push solids off the screen. And we have a short video here showing inlet of a center flow band screen and outlet after solids have been removed. And it gives a good example of a working and well operated offloading process. So next I would like to cover a case study utilizing the practices discussed, followed by a summary. So in this case, we have a dual stage screening system for membrane pretreatment, and this included a sluice configuration. This was installed in 2015 at a plant in Ohio with a flow rate of 44 million gallons a day. This was one of the largest flat sheet ceramic MBR systems in North America at the time. And in this case, on-site testing was used to determine the optimum coarse and fine grid sizes. And the coarse was 6 millimeter, followed by the fine stage at 2 millimeter. And this design utilized a vertical screen design with narrow channels, so it was an extremely compact footprint. It included 3 trains, show 3 trains here, each with 1 coarse and 2 fine screens. And the screening equipment was optimized hydraulically. So looking at the hydraulics, that required more screening area for the fine screens. In this case, we used a trough, um, in this case, a dual trough, to connect all the screens and carry the screenings to compaction. And wastewater is carried to compaction. And the ability here was designed into isolate a compactor so that one could be taken out of service if that need be. And next, we'll wrap it all up here. So in summary, MBR plants are getting larger, more accepted, and some of the main best practice points include two-stage screening, coarse to fine for pretreatment for a membrane plant. First stage is coarse screening, and the best practice is to determine the best grid and then determine equipment type. On-site testing is used to optimize the grid and optimize capture of the system. In the second stage, the fine screening stage is set by MBR type, and that includes the highest capture screens, which are either drum screens or center flow band screens. Drum screens are best for small flows and they have no intermediate seals. Center flow band screens are advantaged for larger flows and retrofits. They have a vertical design and their footprint is significantly different and smaller. And in all technology evaluations, life cycle cost is the best practice, and that is advocated. And with that, thanks for listening. Please call us. We're located in Clearwater, Florida, or email us, and we can be reached at any time. We'd like to answer your questions. Thank you.